Recall, the only property of indefinite integrals is linearity. Definite integrals has many properties. Most of those properties are results of their connection to areas. Definite integrals has also the properties of the indefinite integrals, which mean linearity. And here is a list of the properties. The integral of f(x) dx between a and b equals to the negative of the integral between b and a. This allows me actually to switch the limits of the integral. It's okay to switch the limits, but then don't forget the negative one. The integral of f(x) dx between a to a is 0. Makes sense, because there is no area on the interval a. For any c greater or equals to a and less or equals to b, the integral between ab equals to the integral between ac plus the integral between c and b. This is one of the most useful properties that the finite integrals have. Because I can decide, for example, to take this c because it's between a and b, and instead of evaluating one integral between a and b, I can get two integrals. The first one between a and c and the second one between c and b. And then I can repeat on the process, so actually I can chop any interval ab to as many subintervals that I like, and each one of them will have its own integral. If a function is greater or equals to 0 and x is greater or equals to a and less or equals to b, then the integral of f(x) dx between a and b is greater or equals to 0. We already know that. This just means that all the area is above the x-axis, and we know that the finite integral of those guys is exactly the area, and area cannot be negative. If f(x) is greater or equals to gx, and again we keep the order of a to be less or equals to b, then the integral of f(x) dx between a and b is greater than or equals to the integral of gx dx between a and b. Again, let's look on the areas. The area of the region that enclosed under the curve y equals fx on AB, as you can see, is more or equal to, if they were equal, to the area of the region that is enclosed under the curve y equals gx on the interval AB. And what happens if fx is greater or equals to m and less or equals to capital M, and again a is less or equals to b? Then m times b minus a is less or equals to the integral of f(x) dx between ab, which is less or equals to capital M times b minus a. So here is the situation. Here is the line that represents y equals capital M. As you can see, m is greater or equals to fx on the interval ab. And this line represents y equals m, when m is less or equals to fx. You can see pretty quickly that this area of this region, which is m times ab, you can see now that the area of this region, which is just a rectangle, with length of b minus a and height m is less than the area of the region that enclosed under the graph of fx on AB, but this one, the area of this rectangle, which is b minus a length, and height of capital M, is greater or equals to the area of the region that is under the graph y equals fx on the interval AB. Example. Let's find the integral fx dx between 3 and 5, given that the integral between 0 and 3 is negative 3, and 2 times the integral between 5 and 0 is negative 8. We will have to use some of the properties. Note that in general, the lower limits of the integration do not have to be smaller than the upper one. Like for example, look what is given here. 2 times the integral of fx dx between 5 to 0 equals negative 8. Because I recall I can always switch that. So from here, I get, first of all, that. Okay, I can just divide both sides by 2. And now I can switch the limits of the integral, and I get that the integral fx dx between 0 and 5 equals 4. Now we want to observe that we have x values, and those are of what? Look at all the limits of the integrals above. Okay, so by order, 0, 3, and 5. And the largest interval is obviously between 0 and 5. So here is the interval between 0 and 5. We know that we can chop the finite integrals whenever we want in C between A and B. Because we have here also 3, we know that we have somehow to use this property when C equals 3. Which means that the integral between 0 and 3 plus the integral between 3 and 5 equals to the integral between 0 and 5. Now let's see. You have that? So this guy equals 4. This guy equals negative 3. And this is what we need to find out. So 4 equals negative 3 plus what we have to find out. It means that the value of this integral is just 4 minus 3, which is 7. Example. Let's show that the integral x to the power of 2 dx between 2 and 4 is less than the integral of x cubed dx between 2 and 4. On the interval 2 and 4, it's clear that x to the power of 2 is strictly less than x cubed. Now we are using this property to get directly that the integral of the first one is less than the integral of the second one. If this is 2 and this is 4, okay, you can obviously see that the area under the curve y equals x cubed is more than the area under the curve y equals x to the power of 2. And the reason for this is obviously because x cubed is more than x2, which means that the graph y equals x cubed is above y equals x to the power of 2. Example, the integral of sine x dx between negative pi and pi. Here's the graph of the function. Let's look now at the region that is enclosed between the graph y equals sine x and the interval negative pi pi. Here it is. It's easy to see that the area of the region B equals to the area of the region A. But this integral is the area above, which is B, minus the area below, which is A. So B minus A is 0. Even more, this is also true that for any real number A, the integral of sine x dx between negative A and A will be 0. For example, we can take this, and you can see again that the area of the region C equals to the area of the region D. One is above and the other one is below the x-axis. We notice that on 0 to pi, sine x is greater or equals to 0 and less or equals to 1. So now we are going to use this property to find out something about the area of the region B. When we apply that, m is 0 and capital M is 1. B is pi and A is 0. So we get that the integral of sine x dx between 0 and pi is between 0 times pi minus 0 and 1 times pi minus 0. And we get that the integral of sine x dx between 0 and pi is greater or equals to 0 and less or equals to pi. If f(x) is an odd function, then the integral of f(x) dx between negative a to a equals to 0. This wasn't the case that we have seen. Sine x is an odd function, and we got it, but also x cubed and x are odd functions. And indeed, the integral, for example, of x cubed dx between negative 2 and 2 is 0, and also the integral of x cubed dx between negative 5 and 5 is 0. Also this one is 0, and also this one. And we know already also that this is true to the function f(x) equals sine of x. What happens if f(x) is an odd function? Then, here it is. The integral of f(x) dx between negative a to a equals 2 times the integral of f(x) dx between 0 and a. When f is even, the area on the interval negative 1 and 0 is equal to the area on the interval 0a, and both are above or both below the x-axis. That's why we get that we can break it down at 0. But the first integral between negative a and 0 and the second one between 0 and a are exactly the same. And because of that, we get that. Here is a simple example. For example, we know that x to the power of 2 and cosine x are even functions. It means that the integral of x to the power of 2 dx between negative 2 and 2 equals 2 times the integral of x to the power of 2 dx between 0 and 2. And also, the integral of cosine x dx between negative pi and pi equals to 2 times the integral of cosine x dx between 0 and pi.